Hello, Honors Chemistry, and welcome to Async Day, Snow Day, all those things. So first, obviously, this is the list of things you're supposed to do during class today. So one, you'll do those EOCs, right? This guided practice will help you because, just like last time, you will find that doing these practice will help you with your EOCs. And all we're going to do in this practice, in this guided practice, is run through a whole bunch of Lewis structures. What I strongly recommend is that you practice them and then watch the solutions, although it just kind of depends also on how your experience was with the introductory stuff. And again, all of these will be helpful as you do your EOCs. All right, let's go. All right, so step one, we are going to assess what type of compound we are looking at. NAF is definitely ionic. That's right, ionic because it's composed of a metal and a non-metal, right? So throw back to things we learned back in chapter 5. Now, let's identify how many valence electrons are in each of the species, right? Sodium has 1, fluorine has 7. Now, we know that sodium becomes a cation by getting rid of its valence electron. Fluorine becomes an anion by taking another electron in to fill its valence, which then is going to give us an Na plus and a fluorine with 8 with a charge of -1, right? We'll look at the next one, which is strontium bromide, right? And again, it's ionic, right? We will draw each of the species with their respective valence electrons, and then we'll just reason through the same thing we've been doing since chapter 5, right? Just now, we can put a visual on it, right? Strontium has 2 valence. Each bromine only needs 1 to fill its valence, right? So if strontium has 2 bromines, it can give away its 2 and end up with a charge of 2 plus and a full valence. Each bromine will have a full valence, right? And all the newly formed ions are stable based on having a full valence, where again a valence is the S and P subshell. All right, pH3. Ooh, now 2 nonmetals. That means this one is molecular. So we're going to sum up the total number of valence electrons, 5 from phosphorus, 3 times 1 for those 3 hydrogens, which means 8 valence electrons. Now we're going to draw our atoms, and then we are going to draw a bond between each atom. And again, each bond is 2 electrons, which means that now we have 2 electrons remaining to distribute to fill valences. Here, important to remember, hydrogen's full valence is only how many electrons? Right, 2. A full hydrogen valence is always going to be 2 electrons. Always keep that in mind. All right, next up we've got HI, hydroiodic acid, and again it's molecular. Let's sum up our valence electrons. Hydrogen again has 1, iodine has 7 for a total of 8 to distribute. We will draw our atoms, connect them with a bond. A bond is 2 electrons, which leaves us with 6. And again, hydrogen only needs 2, which means we have exactly enough to fill that iodine valence. Everybody has access to enough to make a full valence, and we are done. And now we have C2H2, right? Where again, it's molecular, right? It's all nonmetals. And so the same concepts apply, but anytime we have a molecule composed of multiple carbons, the carbons will make up the backbone, right? The carbons will be connected to each other, and the hydrogens and other atoms will be distributed around the carbons, often in a symmetrical type of way, right? And so we'll see what that means in just a moment as we draw this molecule. All right, so we will sum up the valence electrons just like every other molecule. We have our 2 carbons with 4 each, 2 hydrogens with 1 each, which gives us a total of 10 to distribute. Now, again, we have our carbons, which will be connected, our hydrogens, which we'll put sort of symmetrically, and we'll draw everybody bonded, right? Which means we've used 6 electrons. We have 4 left to distribute, right? So we will go ahead and fill valences to the best of our ability. And if we look, turns out hydrogens are full, carbons are not, right? But we have used all the allotted electrons. So now this is one of those times when we're going to have to redistribute. So I will erase 1 pair and put it in between the carbons. Still not full, erase another pair and put it in between the carbons. And lo and behold, now we are done. The perk of drawing them all out first and then adding in the multiple bonds is you won't exceed your number of electrons, right? Which is sort of the temptation when you don't have enough, right? Okay, next molecule. Now we have N2H4. Same thing, right? It's still molecular. Those multiple nitrogens, again, are going to make up our backbone, and then we'll distribute the hydrogens relatively symmetrically, right? Are they always symmetrical in real life? No, but for most of what we're going to stick to, yeah, you can that's often going to be the case, right? And so we have 14 electrons to distribute. So again, nitrogens will be connected. We'll distribute the hydrogens around them, and then we'll just bond everybody together, right? And then we will subtract all those electrons from our total, right, which is going to leave us with 4 to distribute. And so we will fill valences by filling those nitrogens. And in this case, now each nitrogen does have access to a full octet, right? Each hydrogen has access to its duet, and we are done, and that is the full and complete structure for N2H4, right? And last up, we have phosphate, right? PO4 3-. Now, this one is different because it is an ion, which means we have to take that into account. Same thing applies, right? If something is an anion, it's because we added some electrons. If it were a cation, it would mean we had subtracted a few electrons, right? So it's molecular. We will sum up our valence electrons like we always do. Since it's a 3- ion, we will go ahead and add 3 more electrons to our tally, right? And then that is the number of electrons that we have to distribute throughout the molecule. All right, so our atoms are out, and then we will connect them all, and we will subtract those electrons. Then we will use what remains, which is 24, to fill our valences. Turns out each oxygen has access to 2, which means each oxygen needs 6. I have 4 oxygens, which means the 24 will perfectly fill all of the oxygen valences. And then if we look at phosphorus, phosphorus already has access to 8, so this structure is complete and correct. And then we will use brackets and 3- to indicate our complete molecule. Again, here is that list of EOCs. And if you finish that, work on chapter 10. All right, thanks for listening. Be good, and I will see you soon. Bye.